Hi guys, this is section 9.13, chemical equilibrium in solutions. So let's look at our generic equilibrium reaction, AA plus BB in equilibrium with CC and DD. The equilibrium condition is that the sum of the chemical potentials for each species each times their coefficient from the balanced equation has to add up to 0. Specifically for our generic equation, it would look like this, where these lowercase letters are the coefficients and the chemical potentials of each of the different species. The reactants, the coefficients are negative because we're losing them, and positive for the products. We also know that we can write a chemical potential in terms of the chemical potential of the pure substance plus the RTLN of the activities raised to the power of their coefficients. So writing this out explicitly for this generic equation, it would look like this down here, where this term is these four terms right here, and this is that term right here, where we've done the sum explicitly. Now, using the properties of logs, we could also write this term in brackets as this ratio right here. So we can take that, and we think this part right here, really what this is this is our delta G, because delta G is the delta, the coefficients times the chemical potentials. So we can say delta G reaction, standard pure substances plus RTLNK equals 0, or delta G equals negative RTLNK. Here K, okay, this is what the whole point of this section is. It's this term right here. We can write that this way down here. This capital pi stands for the product. So what it means is each of the terms inside of the, after the pi, they're all multiplied by each other, like a sigma for a sum, but this is for a product. And we could write the activities in terms of the activity coefficients times the concentrations, where this concentration is, it could be pressures, it could be, whatever. So this generic equation applies to gases, liquids, solids, dissolved species. If this is a gas, by the way, the activities are the fugacities, divided by the fugacity of one atmosphere, or 1 bar, excuse me. We could also write this in terms of molarities or molalities, typical units of concentration. And for a dilute solution, we're going to apply Henry's law of standard state, Henry's law of standard state. And for a dilute solution, the coefficients will be so close to being equal to 1 that we can just say set them equal to 1. And so now that whole activity coefficient term becomes just 1, and we get this, which is really what you guys are used to seeing in terms of equilibrium constants. So for example, for our carbon dioxide and beer equilibrium we talked about before, which is this one right here, the equilibrium constant looks like this. And here are the coefficients. Carbon dioxide has such a low solubility in an aqueous solution that we can say that it's so dilute that the activity coefficients are all 1. So they become 1 here. And we just get the ratio of the pressure to the molality. Notice that this is the vapor phase, so we used pressure. This is solution, so we used molality. We could have used molarity if we wanted to. And that's that.